All right, thank you for your patience, folks. So we have quiz 2 here. I've got my answers. Let's hear yours. So question 1, what is the pattern of variance and covariance that a compound symmetry model would predict, and how many parameters does it have? 2. What's the pattern? Constant. I would also take same. Same variance over time, same covariance over time. 2 parameters regardless of how many occasions. That's a good one. Next question was unstructured. Let's see here. What's the pattern unstructured would predict, how many occasions, and when can it not be used? Only balanced data. What does balance mean? It's not about missingness. Nope. That's yet another thing. Yeah. Interval. So it's not equal interval, and it's not that it has to be complete, but the last word you said, schedule. What do you mean by that? The measurement schedule. So yes, people have to be measured on the same schedule. That's balanced data for an unstructured model to be possible. Not necessarily. So you could have an unstructured model that has 1 unit in time, 2 units in time, and then 6. Because everything gets to be what it wants in unstructured. That's the pattern. So it doesn't work as a function of a time lag. Yes, so that's the other part of it, right? Everything gets to be what it wants. So if I have 4 occasions, how many parameters does an unstructured variance model take? 10. And how did you come up with that? That's it. Number of variances plus number of covariances. And you can either work out the math and count or memorize that formula. Yes, good. Third question, heading into the review for our current homework. How does the content of the variance and covariances in the R matrix differ when a G matrix is included? So let me break that down, right? We have a lot of vocabulary in that sentence. So we have a marker that doesn't work. There we go. G, R, and another letter up here. All right, see some new vocabulary, right? G goes with which level? 2, correct. Level 2, which means R must go with level 1. And V is what you get when you put them back together again. So this is like the combined prediction across levels. So that means that what kind of variance goes in G if it's level 2? Random stuff, random intercepts, and starting today, random slopes. So I'm going to put the letter U here. That means I need to put what letter here for R? E, yes. I've been using the letter T to convey total in models that don't have this distinction. So you can put that in that column here too. So then, after getting that framework in mind, the question then is, how do the content of the variances and covariances in the R matrix differ when a G matrix containing at least a random intercept variance is used or not? Okay, who wants to give me an answer? I didn't say it had to be right. I said it had to be an answer. Sir, you're looking at me. You want to talk, I can feel it.
I was thinking about it. So when you add a G matrix and a random intercept of it reduces the coefficients, right? Because you separated the variance out into 2 piles.
Yes, so you're putting the variance in 2 piles, right? You're taking the random intercept, which we just said earlier was constant variance and covariance, right? It's the most largest source of covariance. That's going over here in G. So then what's left in R has to be smaller, right? Because V is what you get when you put them back together again. So More specifically, the smaller part that's left in R is residual variance and covariance. So you're then talking about what is the pattern of the E's specifically, not the pattern of the total. And this is helpful because then that pattern that's left for the E's, for the residuals, for level 1, can usually be simpler than trying to structure the whole pattern of all the data simultaneously. So yes, using a random intercept allows this separation into piles or levels. You can think of those as somewhat interchangeable phrases, so that you can then focus on the structure of the residual variances and covariances specifically. And there's some essay questions about this towards, not essay, drop-down menu questions towards the end of the homework that are focusing on this distinction. And generally, if it's a model that has R only, so if G is not being used, then R is V. And so all of the words that you would talk about with respect to variance and covariance would be total. The total variance and covariance has a Toeplitz pattern or an unstructured pattern or a compound symmetry pattern. Once you introduce a random intercept variance in the G matrix, then the language that you use to talk about what R is changes from total to residual, from both to just the level 1 part. Good. All right, someone had a question about that, I think, that was relevant. Tiffany, where are you at? Yeah, did that answer your question? Not yet?
Yeah,
not yet. Okay, I'm just checking. I don't want you to think I forgot about you. All right. So we'll answer your question then in just a second. Any other points of clarification I can make on question 3? All right, question 4, pants. I'm trying to make this something you can remember. That's the goal here. It's a completely arbitrary analogy, but I'm going to stick with it. Unstructured is like what kind of pants? Yes, sweatpants or athleisure. I would also accept yoga pants or track pants, right? Something that will always fit, but which is not always appropriate. In contrast, the most limiting model, compound symmetry, skinny jeans. I would also accept jeggings, which are just wrong, as far as I can tell. AR1, autoregressive. The what? The cuffed kind, yes. Tapered jeans or peg roll jeans to create a tapered look, yes. It gets too narrow too quickly at the bottom of the pants and at the matrix. Toeplitz. Yeah, I'd go with straight leg or boot cut, because the idea is that when you have boot cut, sometimes it means straight leg and sometimes it goes out. It can adapt to whatever the style is. So I go with Toeplitz for that. And anything involving a random intercept, I said, is like doing what? Go into a tailor. Rather than trying to fit your entire lower half off the rack, you take out the biggest source of potential misfit, the biggest source of correlation, stick it someplace else, and then go to a tailor and get the rest of it fitted. That's the idea. All right, so those structures are appropriate menu choices for longitudinal data that is primarily characterized by fluctuation. Things where you sample over time just to get a lot of data from the same person, but it doesn't really matter so much if it's time 1 versus 2 versus 3 because they're not changing per se. They're just varying relative to their own internal homeostasis. So the random intercept provides that sort of operationalization, that's too many syllables, idea, let's go with that, of homeostasis. That's the random intercept. It's sort of the level that you're bouncing around. And then the rest of these describe how residuals are correlated across time. All right, that is that. Questions on your learning opportunity otherwise? Okay. Questions on your homework then? I have, let me see here, I have homework 3 pulled up for you, And let's see, since I haven't gotten to your question yet, Tiffany, remind me what your question was?
I was just wondering if you could go over like what the test statistics would mean, like why maybe the correlation or variation.
So you're looking at the last section probably, right? Aha. Okay. So these questions 36, 37, is that where we're at? Okay. So these questions are getting at this idea here. Whenever a model with a random intercept fits better, that implies that there's something different about the pattern of residual correlation than the pattern of total. So without giving the answer away, see if there's anything else I can say here. Well, if I have my tapered genes model, right, that would be an R only AR1. That model says that the total variation is the same across time, and the total covariation is described by an autoregressive pattern. And I say total because if I don't have a random intercept, then R and V are indistinguishable. Whereas if I have a random intercept in G plus an AR correlation in R, then the total is a mixture of the two. The total correlation that shows up in V is partly because of my random intercept, that's the constant part, and then there's an extra part because of the residual correlation that's induced by the autoregressive. That's about all I can say without giving the answers away completely. Does that help at all? Okay. Other questions since we have this up?
I'm stuck on number 18.
Yeah, okay.
There's some unique way of looking at it.
There shouldn't be anything unique, so we're saying I have 18 here. Heterogeneous variance model. So, and we're talking about AR versus toplets, excuse me. So that would be the information from number 14 versus 11. So you should be using those log likelihoods and figuring out how many parameters different they are. Yes, and treating them both as heterogeneous. So yes, the autoregressive pattern is a nested model relative to toplets, because toplets says that each off-diagonal needs to be a different thing, whereas autoregressive says no, it has a pattern to it. It's a square, it's a cube, it's a fourth, it's a fifth. So everything, each gets to be different is the larger model, and then no, they follow this exponential pattern is the nested smaller model. Other than that, I'll have to look at your math and see if I can help you figure out what went wrong. So, but yeah, there shouldn't be anything different about it. If you haven't gotten to this section yet, I've had several questions about which one do I use for questions 17 through 20. Use the REML ones that go through 7 through 16. So, other questions? All right, so this morning, I put up the next homework. I have decided to make it due on the 20th rather than the 13th. Given that we're about a day behind and we're going to hit this week, I have a conference and then fall break is getting in the way of things. I decided not to stress about trying to get through the stuff quickly. So it is going to be due on the 20th. And I've also added in my code a thing that says when the due date is at the top of each of these here. This homework that you're going to start working on after finishing your current homework 3 is very different than homework 3. Homework 3 had nothing to do with SAS, and it was all about trying to understand model comparisons, model names, parameters, likelihood ratio tests, and that kind of stuff. This one is the opposite. The entire point of homework 4 is to get you used to reading SAS output for multi-level models. That's it. There's very little computation. The models themselves are very, very straightforward because they are going to look exactly like the example I'm going to show you. You just have to learn where all this stuff is in your output. That's your goal. And then based on doing the same 3 models in ML and Dremel, answer a couple of questions generalizing the results, comparing the 2. And that's it. So it should not actually take that much time or be that difficult. It's just designed to get you used to looking at the output and knowing where to find things, because SAS output is not labeled in a very user-friendly way, for better or worse. All right. Yeah. Any other questions before we switch gears and start something new? No. Oh, just as an update, what I was doing while you guys were doing your quiz was grading your revisions to homework 1. So I believe I am now caught up. If I asked you to fix anything, please remember to submit it to Blackboard by Friday to get all of your points back. If you submitted something early and you still haven't got all your points, I left a note in there saying that I'll give you another shot to fix it, because what I want you each to have is a complete correct file that you can then pull from in the future as examples of how to do things. So that's why I'm trying to make it to give you the most incentive possible to make all the little fixes. That way it's all correct for your own records. So let me know if you still have questions about any of that. Otherwise, please get it done by Friday. All right. So yes, here's your homeworks in here, making friends with SAS. If not, then let's dive into lecture 5 and example 5. This is going to take us to 3 classes easy to get through, but this is where we get into the really fun stuff. I don't even have to talk about pants or painting or anything to make this interesting, because this is the cool shit. This is the stuff that I get really excited talking about. So, and those of you who have longitudinal data where you're focused on change, which is a lot of you, you will be able to find this stuff extra cool. Those of you who are focused on variation, this is still cool. Just think to yourself that rather than talking about random effects of time, you're going to be talking about random effects of other time-varying variables, the things that you're collecting daily or hourly or what have you. So I'll try to make those extensions work together whenever I can. So I've got lecture 5 up here, and away we go. So back to this picture. We talked about on the right side fluctuation last time, the last couple classes. Now we're talking about change, and we're going to be here for a while. This is going to be chapter 5 and chapter 6, which are some of the longer ones. So when I say change over time, I want you to think about each side of the model separately. This whole model for the means versus model for the variance distinction that we've been making carries through to these ideas as well. Model for the means, our job is going to be to try to find parameters that describe what kind of change happens on average. Are people going up or going down? Are they going up in a continuous fashion, or does it look discontinuous? Is it linear or is it nonlinear? All of those kinds of choices. How do we describe change over time on average? That's what the fixed effects in the model for the means are going to be doing. On the other side, we're still going to have compound symmetry and unstructured as our worst and best fitting baselines, the latter only being available for balanced data. But now we're going to have new patterns. So rather than talking about non-constant covariance and variance because it's AR1 or Topolitz or whatever, we're going to have random slopes for time that do the same thing. They induce non-constant variance and covariance. At the same time, they do so in a substantively meaningful way. They allow us to express which aspects of change show individual differences. Does everybody have the same slope, or do people need their own slopes? Does everyone decelerate at the same rate, or do people slow down in their rates of change differently? Those are the kinds of questions that we then put into the model for the variance. And this is the part where we leave ANOVA behind. ANOVA doesn't do random slopes. That's not a thing. ANOVA does random intercepts, and that's it. So from here on out, there really is no equivalence with the repeated measures ANOVA models that we started with. So first side then, model for the means. You know two. You know these words very well after your last homework, right? Empty. No change. One parameter, fixed intercept. That gives you some mean for your outcome variable that allows the mean to be different than 0. On the other side of the spectrum, so that's the worst fitting model, the best possible fitting model is saturated means. As many means as you have occasions. This is only possible for balanced data. Otherwise, you'd have to have a separate mean for every unique value of time, and it may not even converge. So the same ideas show up on both sides of the model. We have this spectrum of worst to best fit on the mean side, just like we have a spectrum from worst to best fit on the variance side that's described by compound symmetry and unstructured. So the thing that we're going to be picking up then are in-betweens. Why would we do something other than saturated means if that's possible? So in our example, the ANOVA example, I have a 6 occasion data set. I could estimate a saturated means model for my 6 occasions. And we could see whether or not people improve in response time. That was the example between time 1 and 2, 2 and 3, 3 and 4, 4 and 5, and 5 and 6. And I could answer those questions. But that method of explanation doesn't really buy me anything if I want to talk about how people change and how people might have individual differences in change and what individual characteristics predict why some people change differently. I need some kind of term that captures the differences between 1 and 2 and 2 and 3 and 3 and 4 and 4 and 5 and 5 and 6. So our goal is to talk about a trajectory. It's to try and find a model that captures those individual saturated means, to draw a line through them that fits not worse than those individual saturated means, but describes the pattern that they get at. That's what we're going for. We're going to start with linear because that's the simplest one, and it's the basis of pretty much every other option. But we're also going to talk about polynomial approaches, so time squared and time cubed, piecewise slopes, which are exceedingly useful for those of you who have any kind of like multiple baseline intervention-y kinds of things where you have like a watch period and then something happens and then you watch them some more and then later you have follow-up. Those kinds of segmented time structures work very, very well with piecewise models, so we'll do an example of those. And then there's also options that are what I would call truly nonlinear. Things like logs or exponential curves or hyperbolic curves or latent basis models in the world of structural equations. There's other ways of introducing nonlinearity besides just time squared and time cubed. So we're going to hit all of that stuff. But the big, big picture is that these are fixed effects related to some kind of time variable. Their job is to tell us what happens on average. How do we describe mean differences over time? Same idea, other side. So in trying to describe V, in trying to describe the total pattern of variance and covariance across time for your sample, we have choices ranging from the simplest random intercept only, compound symmetry, all the variances are the same, all the covariances are the same, and there's only one reason for covariance, and that's random intercept. To the other side, which is, I don't know what pattern this is, just let everything be what it wants. That's only possible for balanced data, and it's not very efficient. So the in-between structures we looked at last time are the alternative covariance structures, the Topolitzes and the AR1s and that kind of stuff. Now we're looking at in-betweens as formed by random slope models. So they're doing the same thing. They're trying to get this as good a fit as unstructured. That's the goal, not significantly worse than unstructured. We only can make that comparison, though, for balanced data. Okay, with me so far? All right, notation. So do you remember this picture? Two-pile model? Or if you're in a job interview, what is this called instead? Variance component, right, instead of pile. And distinguishing inter-individual variation from intra-individual variation, right? Those are the fancy words we put on this picture. I'm going to stick with pile. So level 2, random intercept variance, individual mean differences. Why do some people have higher means than others in their outcome? I don't know. It's an error term. We're going to try and figure out why. Level 1, within persons over time, residual variance, individual fluctuation within a person around their own mean. Why are you off your line today? That kind of idea. This same model we can write using a different style of notation, which is the multi-level model. Dun, da, da, da. It's October 2nd, and finally you see your first multi-level model in an equation, although we've been talking about it for weeks now. This is going to require a stick. So this is a way of writing the ideas that we've been talking about. It's a language. It is not different. It is helpful in some types of data to write it this way, and we will use this structure predominantly throughout the course, deviating from it only when it's no longer convenient. GLM empty model. So this is an empty means random intercept model. If that we were writing this for single occasion data, I'd have one y per person, so y gets an I subscript. The model for the means would be just the fixed intercept beta 0, which does not have a subscript because it's the fixed intercept. It's the part that everybody gets. And each person, if they have only one y, would have only one e. In longitudinal data, we're picking up a time point within a person as part of the level 1 notation. So now this is specifically our level 1 model. Y at each occasion t for each individual I is a function of a beta, but note this thing is not red. It picks up a subscript. This is now a placeholder for how each person gets their own mean, their own random intercept. Beta 0 I is itself an outcome at level 2. It is not an estimated parameter. It is a placeholder for 2 estimated parameters that are shown here in red and blue. Red for the model for the means, blue for the model for the variance for the next set of slides here. This Y-looking thing, that's gamma. It looks different in different fonts, but in general, it'll have sort of a either Y or V looking structure. It's lowercase gamma. I'm following the same notation that shows up in pretty much all the other multi-level modeling books that I've read before. It gets 2 subscripts, 1 for each level. We start counting at 0 with subscripts. So in these 2 numbers here, we have 2 zeros because we're predicting beta 0, and this is the first term that goes into beta 0. So the order of the subscripts is level 1 and level 2. That will make more sense once you have more gammas in the picture to understand. So this is my new fixed intercept. This is the part that everybody gets, gamma 0, 0. U0I is still my random intercept. Each person gets 1 random intercept, which is the deviation between the grand mean, given in red, to get to their person mean, given in the sum of the 2. So each person gets their own mean by starting with the part that everybody gets, the fixed intercept in red, adding to it the deviation, So if I'm above everybody, my deviation U is positive. If I'm below everyone else, it's negative. Those two get added together, substitute back in for beta, come back down to level 1, and then we pick up the E, which is per time per individual. So the way that we've been writing this, I refer to as a composite equation. It's in the lower right corner of your slide here. The part in parentheses is the part that the beta 0I does. It's just a holder for those two ideas. It's how each person gets their own intercept. They get it through a combination of fixed plus random. So this total model has 3 parameters. Empty means fixed intercept, 1. Model for the variance, random intercept only. We always have a random intercept only as opposed to random intercept plus slopes. We have an E variance at level 1, a U0 variance at level 2, never any covariances across levels, and so just 3. So this is the first model we estimate. We do so to figure out whether or not we actually have longitudinal data, right? Here's what a saturated means model would look like using this same notation. You will very rarely see this, but I've had questions about it before, so I put it in. Let's say that I have 4 occasions. A saturated means random intercept model would have 4 terms in the means model, 1 intercept plus 3 mean differences. In this notation, I'm setting it up so that the last occasion is the reference. That's what happens in SAS and SPSS if you tell it the time is categorical by using the class statement or the by statement. So that's gamma U0 would be my expected mean at time 4. It has a random intercept deviation off of it, so each person gets their own predicted mean at time 4. And then the rest of these, there are 4 betas total, beta 0, beta 1, beta 2, beta 3. That means there's 4 level 2 equations, 1 per beta, always. If you look at the equations for beta 1, 2, and 3, these sort of look redundant because there's only one thing there. So I've written it this way so that I can make that point explicitly. Gamma 1, 0 is the mean difference between time 4 and time 1. Gamma 2, 0 is the mean difference between time 2 and time 4. And beta 3 is the mean difference between 3 and 4. The fact that these don't have any blue terms attached, the fact that there's no extra U's, means those mean differences are predicted to be the same for everybody. So each person gets a random intercept that allows them some difference in intercept that carries through all of their data, but they all change the same. So that's that compound symmetry pattern. Equal variance over time, because the only reason that you would have individual differences is in the intercept, and that's it. Equal covariance over time as well. So using our G plus R plus V patterning here, this is what this model will look like. So V is variance put back together again. I have my random intercept variance in G. It gets pre and post multiplied so that it's the right dimension to be added to R. For now, you can just picture this random intercept variance being added to every single element here. So I have level 2 plus level 1 gives me this combined V that has this pattern that we've seen multiple times. Compound symmetry, equal variance on the diagonal, equal covariance on the off diagonal. If I convert this covariance to a correlation, I get V core in SAS, gives it to you. That correlation has a special name. ICC, yes, intraclass correlation. It's an effect size for how much of your variance is due to person mean differences. person dependency of a particular kind, mean differences, constant dependency. So what value of ICC means game over for your longitudinal analysis? 1. Yes. That would mean all of your variation is between persons, is cross-sectional, is mean differences, is would have been there if you asked them once. That's what 1 means. Anything less than 1, play ball. What's the lowest it can be? 0. Yes. If it's 0, that means you have no random intercept variance. You have no person mean differences. But that number will come back above 0 once you start explaining e-variance though, so it's not going to stay 0 for long. Now let's put time in the story. So 2 sides of the model, 2 jobs for time to do. First question, is there an effective time on average? Is there change on average? That's what fixed effects of time are for. Second question, new part ANOVA can't get you. Do people change differently? That's a random effect of time. So up to this point, we've had fixed versus random intercepts. Fixed intercept is the mean intercept. Random is how far off yours is from fixed. Now we're going to have fixed and random time slopes as well. Please ask me a question. It is, stop, not between. Not between. This is a fixed effective time at level 1 because you're showing persons within persons over time. But the idea is that that slope that you're drawing is the same slope for everybody. That's what the fixed part means. If you add a random part to it, then people get their own slopes. I got a picture. So yes. So fixed and random effects of time, you can have either, both, or neither. So this page has random intercepts in every cell. In each of these pictures I'm going to show you, the x-axis is time. Y-axis is whatever you're measuring that changes over time. Heavy black line is the line generated by a saturated means model. It's the mean trajectory over time. And then the individual people are represented by the individual lines. So if this is your picture, this describes a situation in which you have neither a fixed effective time nor a random effective time. No fixed, because on average, the line is flat. People are not changing. No random, because they're not changing the same. People don't need their own slope. That flat line works for everyone. They do need their own intercept, and that's why they have an intercept shift on the y-axis. So people have their own intercept. They don't need their own slope. And no one needs a slope, in fact. On average, there's no change. This is what I would expect in any kind of fluctuation data. So several of you have like daily diary kinds of studies, or multiple times of affect or activity levels or things like that across days. If you're not trying to fix somebody, if you're just observing them in their natural environment, or you're asking them to report about themselves in an observational design, this is what you should probably get. They're not changing. That's okay. Now, if you designed your study for change and this is what you get, then that's bad news. So no fixed time, no random time. Here is yes fixed, no random. Now, on average in this picture on the top right, there is change over time. That's what the fixed effective time is going to give us. But everybody changes the same. That positive slope holds equally for everyone else, to the best of my PowerPoint drawing ability. Parallel lines. Wow, I cannot talk today. In my defense, Huey had a nightmare at 12:30, so, you know, It's like, yeah, he gets right back to sleep, but me, not so much. So yeah, I'm going to rationalize every time I misspeak. It's his fault, always. It's never my fault. So yes, parallel lines. How's that? Just make up new words. These two pictures are the only instances in which some kind of repeated measures ANOVA is okay. These two pictures show a compound symmetry pattern. Constant variance, and it's going to be constant covariance, although that's harder to see from the picture. Bottom left, the most interesting cell, and yes, this can totally happen. No fixed, yes, random. Is anyone here trying to collect longitudinal data for their dissertation? Amy, she's like, is it like a treatment study? No? Okay, good. All right, well, can you make it one just so I can have an example? No? Okay, well, can we pretend? Okay, great. So Amy's going to do a treatment study. She's going to cure, what would you like to cure today? Okay, she's going to cure diabetes single-handedly with the best dissertation ever. Okay, so she's designing a treatment study. She does random assignment. She goes and gets some people. She fixes them as best she knows how, and after, let's call it 3 years, right? That's a good dissertation. It's an ambitious project. After 3 years, she measures them for the last time. She runs her analysis of variance to find her main effective time is non-significant. Wah, wah. 3 years of your life down the drain. Or is it? Or is it? On average, no fixed effective time, no change on average. Big however. That's because there's a random effective time, and in this picture, some people go up while others go down. That flat line is an artifact. People need their own slopes. What if the control group kept getting worse and worse and worse? We're gonna call this what? Glucose or something that's bad, right? Yeah, that's good. Yeah. See, I do know a few things, only from other people's data that I've played with, and I had to ask, should this go up or down? And they tell me glucose is bad for you. So the control group's glucose kept going up and up and up, while the treatment groups got all better because this is the best longitudinal study in the history of the world. And once you put in group as a predictor, then hopefully that will explain why some people go up and some people go down. So no change on average is not game over. You can have a random change. People can need their own slopes even if on average there's no change. And last but not least, both. On average, in this picture on the bottom right, people go up, but they go up to a different extent. And this is the situation that most longitudinal researchers would have in mind in designing a longitudinal study. They expect some sort of change. They're interested in seeing to what extent it differs by people, and to what extent they can either control or explain those differences. So, 2 questions. Is there change on average? That's the fixed effect. Do people need their own versions of whatever that fixed effect is? That's the random. So if I pick up the fixed effect, there we go, of time into my multi-level equation, I pick up beta 1i. That's another placeholder. That is going to be how each person gets their own rate of change. Note that the variable next to it is time with a ti. That's to convey the idea that each person can have their own set of times. Time is time varying. So more generally, any predictor variable that goes in the level 1 model gets a ti on it. Otherwise, it doesn't go there. It goes somewhere else. Time is measured per occasion per person. Because I have 2 betas, each person gets their own intercept and each person gets their own linear time slope. My level 2 model has 2 betas in it, 2 outcomes. Beta 0 looks the same as before. I have a fixed intercept, I have a random intercept. What differs, though, is the interpretation of the fixed intercept. Before, in the empty model, it was the grand mean. Now the intercept is the expected outcome when the predictors are 0. So this is specifically at time 0, wherever that is. There is no wrong place to put time 0, only weird. I would recommend it's somewhere in your data, but it's up to you where. The beginning is a very common place to put time 0, so you would center time such that you subtract the first occasion's whatever value that is, so you're starting at time 0. If, for instance, in Amy's treatment study, I had year 1, 2, 3, 4, and I wanted to put my intercept at the end, then I would subtract 4, and I would actually have time values that went 0, -1, -2, -3. That's fine too. That's advantageous if what you want to do is predict individual differences in where people end up through your intercept, as opposed to individual differences in where they start. It's up to you. But it's something you got to think about. Where is time 0 going to be for your data? That's your fixed intercept. I now pick up a new fixed effect here on beta 1. This is gamma 1, 0. This is my fixed linear time slope. So you can start to see the pattern for the subscripts here. The first number goes with which beta at level 1 you're predicting. So any term in this beta 0 line is going to start with a 0 in the first place. Likewise, any term in the beta 1 line is going to start with a 1 in the first place for the subscript. When I put the 2 betas back together, the composite equation looks at the one at the bottom here. Beta 0 is these 2 terms. Beta 1 right now is just this one. So I would call this model fixed linear time random intercept to convey the idea that what each person gets their own of is only the random intercept right now. Right now we're saying everybody has the same time slope. It's fixed. It's common. All right. Let me show you, since we're almost out of time, what the equation for the random slope is going to be. So I'm going to skip ahead a little bit and then we'll come back to this stuff later. I'm skipping to slide 19 so you can see the comparison. We've picked up a new error term. Where is it? Where's Waldo? What makes this slide different than the previous one? Yeah, there it is. That thing. That is another pile of variance. That is another level 2 source of variation. That is another way people differ from each other. That is my random linear time slope variance. That UI, is my random linear time slope for this person. It is there to convey the idea that the model has an estimated time slope variance. So it is composed in the same fashion as the intercept, fixed plus random. Fixed is gamma 1, that's my fixed time slope, that's what everybody gets, that's my change on average. U1 is how far off my time slope is from the fixed. Because each person gets their own intercept and their own slope, we also pick up now a covariance between them, and that's going to show up in our G matrix. So let me show you a picture here of what this model looks like. So in this picture, the black line is meant to convey the sample average, and the blue line is for one particular person. So there's my random linear time model at the top. Time 0 is right here at the first occasion. So my fixed intercept, gamma 0, 0, that's the predicted mean at time 0 on average. That's right here. So note it will be wherever this line ends, not exactly what the mean is here, but it's what's predicted to be by the model, meaning the line. Now this blue person, are they above or below the mean at time 0? Below, right? So their U0 is going to be negative. It's phrased as a deviation. Their U0 to get to their own intercept is -4 to get them to their predicted trajectory, which starts at 6. So it's not where their time 0 score is, it's where their predicted time 0 score is based on their own line. The slope on average, rise over run from 8th grade algebra. The rate of change per y over per unit x is 6 on average. Is my blue person growing more or less? More. They started out lower, they're growing faster, so their random slope deviation is going to be positive because they're growing more. So their slope deviation is a +2 to get them to their slope, which is actually 8. And then after giving each person their own intercept and slope, so long as you have at least 3 occasions, that line isn't going to fit their data perfectly. So E steps up to be the difference. So E at time 3, the end here, is negative. E would be positive at time 2. It would be slightly positive at time 1 and slightly negative at time 0. So E is, why are you off your line today? Even after I give you your own line, it doesn't fit perfectly so long as you've got at least 3 occasions. And that's my random slope model. So what this is going to do for us is twofold. It gives us another thing to predict. Why do people start out differently? I don't know. Why do they change differently? I don't know. We can find out. The other thing that it's going to do, and it's going to take a little bit of the scary stuff to show you how it works, is that it makes the variance change over time, and it makes the covariance change over time. And it does so in a quadratic pattern if you have a linear model, in a quartic pattern if you have a quadratic model, and so on. But it creates time-specific patterns of variance and covariance, which get us off of compound symmetry and something closer to unstructured with fewer parameters. So that's the cool stuff. Yay! So, does that help Amy, fixed and random? Okay, all right, I'm not going to see you on Wednesday. I'm going to go give a talk instead. And I'll see you next week on Monday. Let me know if you have any homework questions. In the meantime, keep this in your heads. Fixed, everybody gets the same. Random, everybody gets their own. Keep those 2 words in your head, and the rest of this will be not as bad. So, see you next week, folks.